In this video we're going to look at two things, covariance and correlation. If we have a set of data and we have a set of data points here, including the red one here in the middle, and I'll talk about that in a minute, we have a set of data points. For this set of data points I can find the mean of all the x values and find the mean of all the y values and plot this point. This is the red point here, and then I can divide these, put this line in here and this line in here, and I've divided the data into quadrants. So we've got quadrant 1, 2, 3, 4, a bit like in trigonometry. Now, if I want what's known as, I want some sort of numerical value to describe the relationship, rather than just saying, oh, this was like positive correlation, then I use this term called covariance. Now, the covariance is how far each thing is away from the mean times how far each thing is away from the other mean, like this. Now, for this to be true, here, these values here and here in the first quadrant will be positive, and in these quadrants down here, they're both going to be negative, but a negative times a negative will make a positive. Obviously, if I divide by the number of pairs of points I have, I get the average of those. And this is what the covariance is. So I can see here that most of my points for a positive correlation are in the first or in the third quadrant. Now I can actually move these points. If I move these points so that, okay, the average will change obviously because the value is changing, but not by very much. I can put these points in roughly a straight line. Okay, so they're roughly in a very straight line now. In fact, therefore, okay, so I've got roughly a straight line, and then I can have this thing called the correlation coefficient, which is calculated by doing the covariance divided by the square root of variance of x times the square root of the variance of y. And when I've got almost perfect linear, positive linear correlation, this will be 1. Now, so what describes the sort of relationship between is this thing here called the covariance, and the measurement of that is called the correlation coefficient. Now I can move these points. Let's now move these points by quite a lot. So if I move these points into the second quadrant, okay, you'll be looking at the covariance while I'm doing this. Okay, again, don't forget the means will move. Okay, if I move these down here, which is what I wanted to really do, and then move these three here. Okay, then what you can see here is that the covariance has become a negative value. Okay, this is because one here, the x value will be negative, this will be negative, but the y value will be positive. So negative times a positive gives you a negative, and a similar sort of thing here. The x value here is positive, but the y value here is negative, so this gives you a negative value here. So you can see how this works, and I can also put this in like an almost negative straight line. Slightly under that, I'll just move it away from the means. Okay, and you can see here the value of the purple. You see that we've got a sort of almost negative straight line here, and you can see that the correlation coefficient will be equal to -1. Later you'll do a question where you have to actually prove that using expectation algebra, but you can just see how it works. Now if I move all the points all over the place, so that they're a mixture in all four quadrants, the covariance will get up to be a lower number, and depending, it might just be that's probably as low as I can probably get it. Okay, so I've got the points in all 4 quadrants here, okay? And what I've got here is a very, very low negative covariance, but the correlation coefficient is almost 0, which says that there is sort of no linear relationship here. And this is how it works. I've done even better there. Okay, so this video is like showing you a little bit how covariance works, how it's calculated. This thing, we've introduced the correlation coefficient, and here I've got it to be very low. So almost no correlation here, no linear correlation here. Okay, so we're going to go back now and just look at some formulae. So we've got the covariance is equal to the mean of how far, the sum of how far each point is away from the mean, the x point and the y point, the product of that. If you write it in the language of expectation, it becomes this. It's the same formula, but just using expectation. Okay, this formula is not very useful to use. It's far better to use this one here. So alternative covariance formula is this one. Covariance of xy is e of xy minus the mean of x times minus the mean of y, which is also a much more useful formula to use. Now the correlation coefficient rho is the covariance of xy divided by the square root of the variance of x times the square variance of the variable y. When the data spread out, this becomes a very, very, very low value. So it's like will come very, very close to 0, as I've just shown you. And as an estimate for the sample product moment correlation coefficient, there's this one called R, and this can be calculated using the calculator as well, from I to n of x I y I minus n x bar y bar divided by the square root of I to n of xi squared minus n x bar squared times from I to n of yi squared minus n y bar squared. Now you'll be pleased to know that this formula is actually written into your formula booklet, so you won't need to remember it, but you should try to have a think how it works. Okay, so the idea of covariance comes from taking the mean point, splitting the data into quadrants, okay, and working out how far each thing is away from the mean and taking the average of all those. When the data is all scattered out, this will be very close to 0. When the data is in like a positive straight line here, most of the data will be in quadrant 1 and quadrant 3. And for negative correlation, most of the data will be in quadrant 2 and quadrant 4, and all these quadrants are defined where the mean of both sets of data is. Okay, so this has been a video to introduce you to the two terms covariance and correlation.